All right, thank you very much for the introduction. And it's a real pleasure to be invited here. And I've had a great time meeting many of you and hearing about what you've been doing, your enthusiasm about math. And yeah, the coolest part about this profession is that I get to try, play around with these things that I really find interesting. And I'll try to tell you about one of these fundamental concepts in number theory. So I'm a number theorist today that I'm calling p-adicity, which is a bit of a made-up word, but about p-adic numbers. Okay. So feel free to interrupt and ask questions, and let's get started. So, right. So in the beginning, right, matter of opinion, right? So I feel like in the beginning there was Z. That's my personal bias, right? I mean, the oldest areas of math, at least, probably counting, right? Doesn't have a good argument. Logic, geometry, number theory were probably the oldest areas of math in the culture that I'm aware of. Right, so we think of 0, 1, 2, 3, 4, right? We often think of them on the number line, right? And then we start learning about negatives later on. Great, that's what it is. And that's, you know, when I talk with my daughter who's 7 years old, she loves counting. People are aware of this, right? But then we ask, what, you know, being a theoretical mathematician, what is it really? What really characterizes it? Okay, and that's not something that we love, not just because it's sort of cool, because it allows us to get mileage out of it. And we'll talk about that a bit. So Z, maybe once you think about just collections of stuff, there's lots of other collections of stuff that are like Z. Just you enumerate something and it looks like Z. You've just labeled the model like Z. But Z, the integers, has a ring structure, right? It has a plus and it has a times. And they behave well. They behave well with respect to each other. The distributive law is one of the major ways that they play well with respect to each other. And then in an abstract algebra course, you might hear this definition of ring, where you have this group law, which is the plus that's commutative, and a multiplication law that has a unit called 1, and so forth. But let's try to narrow down what really is Z among rings. Like this is something that we like, not just because it's like a fun exercise. It'll help us eventually do better. It's like we want to know not just like what is Z, it's those numbers, right? But like what is it? It's not quite right, but what does it do? What characterizes it? Well, it's a domain. You can come up with rings that don't have this property, but this one has the fact that if two things multiply to 0, then one of them is 0. And then it also comes along with an order. And I think that's the kind of thing that we definitely start illustrating to like children as we teach them about numbers. Great. But we really want what I currently want what sets Z apart, but Q, the rationals, also has this property. So do the real numbers. And even some things between Z and Q, right? Like if you add in all the fractions, not all of them anymore, but all of them that have only 2 showing up in the denominator, that is a subring of Q, right? You can stay closed under addition and multiplication. It's a ring. And it's not Z. So if I want to characterize it, it turns out that there's this really special thing, the well-ordering principle, that says that any non-empty subset of the positives, and where did I get positive from? I got it from the order, right? Greater than 0, has a least element, like a minimum element. So not only is it less than everything in its subset, but it is in the subset, right? So you could say, how does this not work? Well, if I took any of these examples, what I could do is just take those things. The simplest example maybe is those things that are strictly greater than 0. Right? And then if I take all those things which are strictly greater than 0, it has no least element. What's the least among the positive rationals? There is none, right? You could just divide it by 2 and get a smaller one. That's why Q fails the well-ordering principle. And this is a perspective that I learned from being a counselor in this Promise program, which was based on the Ross program that I think has a lot to do with Ohio State. And their slogan is think deeply about simple things. And that's the starting point. But what's fun exercise then is to do some exercises. How can I build an elementary number theory out of this, right? Elementary number theory doesn't mean easy. It just means it has to do with Z, right? So you could definitely a lot of hard questions about Z, including some that we don't know today. But where you'd start is that, well, if I view this, right, this ordered ring with the well-ordering principle as the definition of Z, I actually have to prove then that there's no integer between 0 and 1. And the idea here would be, like, what's the proof look like? It's a fun one. Like you could say, oh, if I had something funny, if I had some funny integer here between 0 and 1, then what can you do? You think, how can I create a contradiction? Well, I could use the ordering property that plays well with multiplication and then take its powers. And those have to strictly decrease. And then you can get a contradiction to the well-ordering principle, right? And then thereby you can go to mathematical induction. And sort of, a slogan for this is that the mathematical induction, which says that if you, mathematical induction sort of relies on the integers being 1, 2, 3, 4, 5, and what we know they are, right? And once we take care of this, we're all set. Right, so well-ordering principle and mathematical induction turn out to be equivalent in some sense. And then another gem of elementary number theory goes by the name of fundamental theorem of arithmetic sometimes, and that's that we have unique factorization into primes. Like those are some of the crucial structures that we have on Z. Okay, then what comes next, right? So again, matter of opinion, but I think in most curricula, mathematical experience, really just jump to R, right? And why is the real numbers R so nice? Well, because we have the number line, right? So we have this continuum of numbers, has some big landmarks, 0, 1, maybe somewhere out here is something like pi. And we can ask the same question, like what are the axioms that would characterize R, right? And actually the way it works, to really know that they characterize, right? You say, if I had two things that satisfy it, I could prove they're sort of isomorphic in a way that respects all structures. Then, like if you had a Z and a Z prime, they both satisfy the axioms. You have to prove they're the same thing. You can do the same thing with R, right? So an ordered field, right? So a field is something where not only can you, do you have your order, but you also have that for any elements, real numbers A and B, you can divide by B as long as B is not 0. Right? So that's what a field is as opposed to a domain. You can actually divide out except by 0, right? So fields are things like Q and R, right? They have everything that you can get by dividing out. But, we need some additional property, and the crucial thing about R is its completeness. And the way to put it sort of formally is that any non-empty subset of R that is bounded above has a supremum in R, and that's called completeness. And sort of a way to see that Q doesn't have that is that you could start out with, let's say I take all of the rational numbers such that R is less than pi, right? And then you have all these rational numbers leading up to there. They get really close, arbitrarily close, but we don't have that missing pi, right? Because it's irrational. And that's the thing that we sort of want that gives you R. And you can actually, if you have two copies of R that satisfy all these axioms, you can prove that they're one and the same thing, right? So R, we can feel like R is decimals. Maybe if I start, right, Z is the integers, R is decimals. That's what we get out of school math, and it takes us a long way. But these are the things that characterize it when we think carefully about it. So R is, I think Z and R, right, those are the two sort of foundations of math that we see in much of an undergraduate curriculum. Like you can do calculus with these things, metrics, because R is sort of where we believe distance ought to be valued, and we've been convinced of that. Really useful in physics, engineering. And then in theoretical mathematics, we might talk about topologies. There's kinds of analysis that really take us a long way. And then we even start talking about manifolds, right? So it becomes, R is a sort of foundation of shape, right? So a manifold is something that sort of locally looks like there's neighborhoods, and you can cover your space by things that look like, say, R2, or a ball inside R2. Say that your space is a sphere, right? It doesn't look like R2 globally, but locally it looks like an open subset of ball and R, that kind of thing. Right, so that's a notion of manifold. And, right, so that goes a long way in math, but then what, there we go. But I'm going to take things a different direction. Before I do that, I want to just put in our heads very clearly this notion of metric space, that exactly is a way of saying what's a space, a bunch of stuff, a set, and then a notion of distance. And just to review this, right, I'm going to view them as two axioms, right? And the first, number one, is sort of a really fundamental thing that when we think of a notion of distance between points x and point y. One is that if there's zero distance between them, then they're the same point. That characterizes it. And that it's symmetric. You see the distance from x to y is the same as from y to x. Okay, but then the next thing that fits our intuition for distance on the globe or on a flat plane is the triangle inequality here. All right, if you go from x to y, but then you maybe detour it off to z first, you can't like find a point z that somehow gives you a shortcut. from the original distance. Okay. And then what we're going to be interested in a little bit, especially with the rational numbers, is an absolute value is like a metric, but when you have a zero. So think of some vector space or field, anything where you have a zero, the absolute value is your distance from zero. And then this gives us another perspective on R, a completion of Q according to our usual metric. So we had this former notion of completion, and it was sort of we have to fill in an upper bound. Like we really have to have, if you have any collection of rationals that's bounded above, we have to have that upper bound. But then a perspective that we can get out of this is this notion of Cauchy sequence. So a Cauchy sequence is any sequence where you get, as you proceed along your sequence, you get arbitrarily, the terms get close together. If you've taken a analysis course, you maybe, right? So a sequence of, say, rational numbers, you call it Cauchy when as time goes on, they get arbitrarily close together and stay arbitrarily close together. But that doesn't mean they have a limit, say in Q, right? You could have a sequence converging to pi, right? So you can have a Cauchy sequence of things that are getting really close, but they don't converge. And then the completion is that you sort of add in all the limits of Cauchy sequence. Add limits of Cauchy sequences. And I'll be more precise about that in a little bit. Okay, so I just wanted to put in your mind what is a metric space and what is a completion. We want to have all these limits existing so you could actually just formally add them if they didn't already exist in there. Okay. Now, the thing I want to suggest with this notion of p-adicity and how it's going to come up is what if we did something else next after z? Right, so here's the key question that opens up the door to this. Is there a notion of distance on Q? Right, so we got our real distance, that's great. Other than the usual one, this is our standard distance between numbers, our absolute value, right? That respects the arithmetic structure plus and times, and isn't the one we're used to. So I wrote down a definition of respecting arithmetic structure, and this first axiom we think of as much like the first axiom before, distance between two things. If you can go back to a metric this way, you can take the norm of the absolute value of the difference. So this sort of encompasses the first axiom before, symmetry and non-triviality. And then we have the triangle inequality, which looks like this when you think about, say, adding vectors. And then we do want it to play, that sort of takes care of playing nicely with plus, but we also want it to play nicely with times. So you get this multiplicativity. And then this is an exercise you can do. That if you have a norm axiom, then this distance you form out of it respects all the axioms of metric space. And the answer to this question is yes, because of this phenomenon of p-adic distances. Let me explain what that is. Here p is a prime, right? So p is a prime number. That's a key thing for the rest of the talk. Okay. And there's this new notion of distance, which turns out to be a norm. And it's a funny one. It's really going to be quite different. So we have some rational number. And what we do is we factor out what I'll call the p part. Right? So we have, say, our number is 2. So I'll do an example. All right? So if I have p equals 2, in my little example here, then if I want to look at the p-adic norm of something like 12/5, I would factor out the 2. Or let's write it as 2 to the 2. Right? I'm going to take out that p part, just focus on that p part, and then invert that to get the p-adic distance. Okay? Okay, so this is an interesting thing. What's the intuition behind this, right? So two rational numbers are p-adically close together when their difference has a numerator, very divisible by p, and vice versa, the opposite when you have a denominator, very divisible by p. And the first things, of course, you'd be like, okay, this is interesting. Just the things that we'll move on from at the moment, because I want to give you intuition, but really have to be proved, is that yes, this is actually a norm. It satisfies those axioms. Right, so if I multiply two rational numbers together, their p-adic norms do multiply, and so forth. And then there's another very interesting fact called Ostrowski's theorem that actually says that up to some notion of equivalence, all norms, all norms are p-adic, or they're the usual one. Sorry about that. Are like the usual one, say that, and then union with all of the p-adic ones. So you have a 2-adic distance, right? And these are really different notions of distance, right? 2-adic distance, 3-adic distance, etc. Okay. So what I want to give some sense of, like, the first question you might ask is, like, what does a number line look like here? And the answer is a bit, maybe even frustrating. There's some nice artistic things if you like Google for pictures of this. And the kind of thing that I found sort of convincing is the following. So if you take p equals 2 and I'm trying to get what do these p-adic things look like? Well, I'll start writing down some numbers. Here I have 1 and then 2. And 1 and 2, their difference is 1, which is not very divisible by 2. Right? So these are sort of separate. All right, I'll keep going. 3 is sort of, has distance 1/2 from 1, because it's the inverse of the difference. The difference between 1 and 3 is 2. Its p part is 2, and its 2 part is 2, and then so I invert it, I get distance 1/2. So 3 is actually closer, and we have the same thing here. And then if I keep going, well, 5 is actually closer to 1. So I get this kind of pattern, 5, 6, 7, and 8. And I'm going to draw one sort of another rank of circles, right? So everything that's inside a blue circle has distance 1/4 from each other. Right? So that's like the 1/4. And everything that's within the purple circles had distance no more than 1/2. And then things that are in separate circles have distance 1 from each other, right? So things are sort of getting more close when their difference is more divisible. So it's looking quite different so far. Maybe I'll try one more, like if you do the 3-adic version of the same thing. So I might do 1, 2, 3, and then here we have 4, 5, 6, 7, 8, 9, and then what can I do here? 10, 11, 12. Okay, and then so these 3-adically, so this is the p equals 3 picture. We can circle them like this when they're at least distance 1/3 away from each other, right? Because their differences are all divisible by 3, and then there's a few of them that are even closer. All right, so all these have differences 9, so it's like more divisible. And it actually will turn out I'll say it again, but the completion of Z under this metric is actually not just Z, and it looks like a Cantor set. So if you want some like usual real R-valued intuition, topologically that's what it's starting to look like, but we'll come back to that. So there's some really interesting and at first unusual phenomena that you get in the p-adic world to get like much more exposure to it, right? So actually this series of powers of 2 is going to converge. We can say to what? What does it get really close to? It's like the partial sums, right? What does it mean for a series to converge? You look at it at the partial sums. So it's 1, 3, 7, right? I'm adding 4, then I'm adding 8, then I'm adding 16. And I realize, oh, right, my general term looks like 2m minus 1, but 2 to the m is getting really small, right? So this thing actually converges to minus 1. And actually, this is an interesting thing. You can get some integers to converge, some positive integers to converge to any negative integer, but you have to it doesn't have a sort of finite expansion. Right? Some other interesting facts. The series where you take the sum of factorials is actually, the terms are getting really small no matter what no matter what p your p-adic is. Because your terms are getting smaller and smaller. And it turns out that your p-adic norm has a sort of stronger ultrametric property, which is sometimes called non-Archimedean. And you can actually get that to say that this thing, which is completely blows up in our usual real-based world, right? That's the farthest thing from convergent you can get, right? It actually will be Cauchy. right? We're also saying z is bounded, right? You can't get them to be farther apart than distance 1. So that's quite different than the Archimedean world. And I'm using the Archimedean to mean this term. That's our usual notion of distance, where z is very much unbounded, right? So a lot of times people use ultrametric. They'll say it's synonymous with non-Archimedean, but I'll just try to say sort of positive words, ultrametric and Archimedean. And then another funny phenomenon that you see in the p-adic world with this p-adic norm is that every triangle is isosceles, which is a sort of interesting phenomenon as well. Just wrote one example of this, right? 3 points, take their distances, and you have, I have 2 1/3. And this will actually extend to like multidimensional spaces over QP, not just one dimension. Okay, so those are sort of like fun things we get. Now I'm gonna like spell out for you the thing that I left a little bit vague on a previous slide, and that's how do you actually complete something, right? So actually there's this process that turns out to be uniform, and we can apply it to the p-adic world as well as the Archimedean world where we had the real numbers. So with the real numbers, how did we get them? One way to get them is to say that I can build R, the real numbers, out of Q by taking all sequences that get closer and closer together as you go along the sequence, right? They don't have to be converging to a rational number, but then you actually count that sequence as an element of your new number system, okay? But then you're going to repeat some things, right? You're repeating some of their limits, even if you add in those limits, because there's more than one Cauchy sequence that converges to each thing. So you just count them the same if they're getting really close to each other, okay? So what is the number of pi in R under this definition with our usual norm, right? The number pi would be the collection of all sequences of rational numbers that converge to pi, and you count all of them to be the same because they have the same, all those are getting really close to each other in the long run, okay? Okay, now there's an exercise that you can actually then get plus and times operations to extend to this completion. So it's not just like you're adding stuff, you can actually extend the addition and multiplication operations as well. And with this is how we build, as I said, R out of Q. But then you can also get a completely new, turns out to be a field. You can get QP out of Q by taking all the collection of sequences where the terms get closer together, these Cauchy sequences, with respect to a p-adic norm for any prime p. Right? So we have this whole system indexed by the primes of new completions of Q. And this is so what, in summary, what have we done? We got R sort of out of the order, right? So out of our order of 1, less than 2, less than 3. This is like the Archimedean world emphasizes the order. And then we eventually applied this to rationals. We took limits, we got R. But then the p-adic numbers are really based on this fundamental theorem of arithmetic. Using that fundamental theorem of arithmetic, we can sort of get prime factorizations of every numbers and determine their size, and we get a completely different way of measuring size, right? So those are the two crucial things, right? Children first learn the order on Z, and then on rational numbers, and then one thing that you're exposed to later is unique prime factorization. So that's that other key structure of Z that we're really exploiting now. And we come up with a new notion of completion because of it. Okay, so here are some things we can do with this. In many ways, even though QP, the p-adics are not as familiar to us as the real numbers, and with good reason, right? Like, R is really a great model for distances in the real world and so forth. It turns out that a sequence in QP converges if and only if its terms, a series converges if and only if its terms go to 0, right? That is not at all true in the Archimedean world. So we're starting to feel, oh, actually, things that we usually start calling like basic analysis are easier, actually. Okay, so right, we have this harmonic series I wrote over here, right? This is, yes, its terms absolutely converge to 0, for sure, but it doesn't converge, it just keeps going. And it's that ultrametric, that strong triangle inequality that you can work with and show that this happens. That's the key thing. All right. And then here's maybe a nice analogy with the real numbers, something they do have in common, that there's a unique digit expansion where we start at this index m, and we only allow our p-adic digits to be between 0 to p minus 1. And then let's just take, for example, what were we seeing? If you want to like write, say, 7 two-adically, how would you write 7? It looks sort of familiar if you've done, sorry, p equals 2. Let's write down 7. So 7 is equal to, I think it's going to be 1 plus 1 times 2 plus 1 times 4 would be its unique p-adic expansion. And earlier, actually, we saw the unique two-adic expansion of minus 1. So minus 1 has digits 1, 1, 1, 1, 1, 1, 1, 1, 1 forever, right? So you can get all these things. So you can make p play the role much like 1 over 10 plays in the real world, because we know decimals work quite well to characterize real numbers. But actually, it works better. And just like the convergence is easier, you actually get uniqueness of your digital expansion, right? Like 0.99999, right, is the same as 1. So you have that coming from the altermetric property ultimately again. And then the other interesting thing is that z is now sort of, the z, elements of z are getting really close to each other. That doesn't happen at all within R. And that is the key that really makes a very interesting way that p-adicity like brings together algebra and topology and analysis, because z actually completes to something which has some nice properties, like this thing is compact. And I just want to say it's if you want to see what it looks like, it's actually homeomorphic to the Cantor set. So that's the thing that is homeomorphic to a Cantor set. All right, and then if we say, okay, I want to understand the first few things in this, how if I understand all the open balls, right? That's a really good way to start understanding R. If you've done analysis, you know you really want to work with open balls in R or n-dimensional real space. But then one interesting thing in the p-adic world is that open balls or closed balls, or basically radii that you actually achieve, occur discretely. This is a really weird and interesting thing. And what that means is that open balls are closed as well, right? If you think about your definition of an open ball and a closed ball, they still make perfectly good sense. You probably justified that in your, you might, if you've been in an analysis course where you saw metric spaces, you saw that. And so actually this results in a property that QP and ZP are what's called totally disconnected. I misspelled that. T-O-T-A. So you say that some points are not connected to each other when you can when you can sort of separate them into two components, each of which is closed and open. And this is just really easy to do, right? So I can partition, if I have any two elements of ZP, I can partition it into one clopen thing and one closed and open thing and another closed and open thing containing each point. You can separate everything. Now that actually makes some notions in the p-adic world harder. So maybe that's in some ways it's like, oh, topology is simpler. It's also a bit of bad news. I'll say more about where that is bad news later. Okay, so it really is a different kind of picture. So how far does this go back? People credit Kurt Hensel with discovering the p-adics. He wrote down p-adic digital expansions and worked with them in this paper, A New Foundation for the Theories of Algebraic Integers. I want to talk about one more thing before talking about a cool application of these p-adics, and that's that you can actually extend the notion of limit into algebra. Okay, and actually it's actually a category theoretic concept that gets applied all the time in many mathematical categories. So we can think about these digital expansions and think about how p to the m times zp is an ideal in zp. And we can actually say the following, which is that we can construct ZP in a new and very algebraic way. Not just completing Z anymore, but saying that a system of choices that maps one to the next thing. So what do I mean by this? Let's just say that like p is 3. And I'm going to give you a new way to think about 3-adic integers. Okay, so here we have z mod 3z, z mod 9z, and z mod 27z. And one way to think of what is a 3-adic integer is to say that it's a system of choices of these finite rings. Right? It's like 1, 4, say 4 there, where a system of choices that's compatible one with the next, right? So z mod p to the nz maps surjectively, just reducing by a further modulus. Z mod p to the third maps to z mod p squared, and you can keep doing that forever. And then if you take a bunch of choices going off to infinity, that's actually a new way to get a p-adic integer. So that's probably the way I think about it most. Some people earlier today, some students earlier today were asking me, how do you actually think of these things? The topology is a little, and the completion picture might be a little tough, but this is a nice way. So for example, if you think about what is an integer, like what's the number 4 within z3, it would be this system of choices, but then it stabilizes. Like you just write 4, 4, 4, 4, 4 for the rest of them. But then there's plenty, in fact, there's uncountably many elements of ZP that you get from all these choices. If you've seen the proof that R is uncountable because of maybe decimal expansions, the same thing applies, right? We have P expansions in the p-adic world. And then another thing that's really nifty about this is that this gives us a chance to like relate things in these finite rings. Like sometimes we want to do something, it's easier to do it in a finite ring, as you can imagine. Sometimes these rings are simpler, and we want to understand something over ZP. The idea is that you can sort of take a limit, which we do all the time as working number theorists. So I think, Kurt Hensel wrote these down, but it's this theorem that sort of convinced people of the utility of p-adic numbers number theoretically. Okay, so it's saying a lot of number theory is about classically is about Diophantine equations. If I have some equation in polynomials, can I find a solution in Q or in Z? And here's the idea. This is known as a quadratic form or quadratic equation. The indeterminants are the x's and y's. And I have some of them, but the point is that every single term is quadratic, right? It's degree 2 in the indeterminants. Sorry, I should have just said one collection of x's, excuse me. I don't want to make it separate like that. So the y's should be x's. Excuse me. There we go. So this has a non-trivial solution in Q. That can be a hard question to answer. It turns out it's good enough to find a non-trivial solution in the reals and in QP. Okay? So we can see this as a necessary condition, right? So if you had a rational solution, well, Q is inside of R, and Q is inside of QP for every P. So that direction is clear, but you can actually go the other way. And why is this exciting? It's because solutions in QP, and do you have a solution in QP, can actually be detected often you can detect, and this is actually something called Hensel's lemma. You can use that tower, that limit, how you form ZP out of all the Z mod P to the n's. And it turns out, there's some n that you can figure out for each prime that you can see if this thing has a solution in QP. You only have to do a finite amount of computation. Now that's something you can imagine a computer can do, right? So the idea is actually that these days with powerful computers, p-adics are actually quite computable. I mean, we've designed computers, of course, to handle decimals and deal with approximation and so forth. It's exactly the same in the p-adic world, except sometimes approximation and everything is actually easier. And I'll just say for almost all but finitely many p, you can just actually do Z mod pz. Okay? It's only a finite number that you have to go up higher. So that's why this is exciting computationally. But then this also convinced people of what I'll say next, which is that, yes, there's a great many uses of the real numbers in the Archimedean world, but we should just consider them all to be the same. They're all equally important. They all tell us they're sort of all a system of ways to complete Q and understand number theoretic questions. If you ask something over Q, it can be hard. And the idea is it's actually, even though QP you could say is a harder number field, right? It comes later in your mathematical education. Things are actually easier there. And we can use that because of this kind of computation technique, right? It's much easier to work with z mod pz, or z mod p to the nz than it is to solve things in Q. Okay. So the thing I want to, the summary so far is I'm trying to convince you that this phenomenon of p-adic stuff is a really fun confluence of algebra, topology, and analysis, right? So we definitely do analysis over R. We had to construct it in a certain way. But this idea that this completion with respect to this distance is the same as this purely algebraic notion of limit is a really exciting thing that brings them together. And we can like solve polynomial equations. I want to solve it in ZP. It turns out I can solve it in z mod p to the nz. So from that, you can say, okay, I did all these things in the real world. How if I do it in the p-adic world? And there is actually a lot of that. In terms of metrics and topologies, there are p-adic Banach spaces, and like people study functional analysis and things and have applications for it as well. There's notions of analysis, and I'm going to be illustrating some aspects of analysis for the rest of this talk. I'm going to talk about an application. But I'm sort of taking this break in the middle just to overview what else is done. People also try to come up with notions of p-adic manifolds, things that look locally like some n-dimensional p-adic space, right? Just like a manifold, standard definition looks like a n-dimensional real space. And that is challenging. This is where this fact that every ball is open and closed is sort of inconvenient. And people have to work hard and do more fancy things in scheme theory, and that's a big thing. But so many areas of number theory are really highly touched with p-adic notions. Okay, I just wanted to mention one aspect of that final bullet in the manifolds issue. There's been some really exciting recent work by Dustin Clausen and Peter Scholze. They've come up with a new theory of called condensed mathematics that actually puts p-adic analytic geometry and real analytic geometry into a single framework, which is like a really, really exciting thing to me and lots of other people. Okay, but I'm going to leave that for now and focus on some analysis. All right, so this is basically the start of part 2 of the talk, and I'm going to talk about the Riemann zeta function. Any questions before I go into part 2? Okay, so the Riemann zeta function is, I've seen it in a few student talks and even more general things like the Riemann zeta function, which are called L functions. It has a really strong role in the history of number theory, especially looking at the distribution of prime numbers among the real numbers, right? So that is an Archimedean perspective, and that's good, right? The first thing about it is, right, so what is it defined to be? It's the sum of all the minus s powers of the integers, right? And that is going to converge for s that have a big real part, right? It's not going to converge for s equals 1. That's the harmonic series, right? But then it has this nifty Euler product, right? So we can, if we just assume that everything analytically convergence works nicely, we believe, oh, because of the fundamental theorem of arithmetic, I can make this factorization here. This factorization here, where I say, okay, if I write down powers of primes, I'll get each number once uniquely, right? And then you can do this and do your geometric series formula, and this is called an Euler product, right? And things here are called Euler factors, all right? I'm not going to go so much into the, I'm not going to give the details of the connection with the distribution of how are the primes among the integers, but here are the key things that are the start of looking at zeta of s. First, Euler thought of it as a function of integers, right? But then went on to think of it with Archimedean usual, right, analysis, and particularly complex analysis, okay? So I view complex numbers going just beyond the real numbers, a sort of quadratic extension where you throw in I, right, the square root of -1. And what can we do there? Well, as I've said, the series converges for s with large real part. Remarkably, in the theory of complex analysis, right, that functions are locally expressible as power series, and you can use that and then extend it and say that actually when a complex analytic function extends to like a bigger open ball, it extends uniquely, right? Which is something that's completely not true of like real smooth functions. So complex analytic stuff is remarkably rigid. And it has this problem at s equals 1, but we understand it pretty well. Its power series there does blow up, but it blows up like this. So we say that there's sort of a number 1 here, and we call that the residue of the pole. So it's like very, very clear what's going on there. And there's a reflection principle, right, called a functional equation. If you understand its value at s, then you understand its value at 1 minus s. These are things that Bernhard Riemann wrote down in his 1859 paper, and also stated some more things, such as, I'll just summarize them here, the Riemann hypothesis, right? So the picture of what Riemann talked about was that if I draw the complex numbers like this, here's 0, here's 1, this function has a singularity, it's not quite defined at 1. We do have that the zeta function has value 0 at negative even integers, and Riemann proposed, conjectured, we call it the Riemann hypothesis, this conjecture, that the remaining values at which the zeta function has value 0 are in the middle of this thing that we call the critical strip. So that's the critical strip. And then it was sufficient to prove this prime number theorem, which says that we have an asymptotic expression for the number of primes up to, say, a real number x as x goes to infinity, by ruling out zeros on the sort of extreme line. The extreme being real part of s equals 1. All right. And that's how actually people proved the prime number theorem at the end of the 19th century. Now there is a further conjecture, I'll just say, to summarize the stuff that Riemann came up with. Maybe this is, I don't think Riemann mentioned this, that these zeros are simple, that the order of vanishing for how this function, like its Taylor series at one of those zeros that I'm calling rho, it doesn't vanish to second order. It doesn't sort of look like a parabola there, it really just vanishes to order 1. That's called a simple zero. Right, so I'll say, what does it mean for the zeros to be simple? It means that zeta s looks like some constant times s minus rho, and then plus further powers. All right, and this a needs to be not 0. Right, so zeta of rho is 0. Right, so its sort of Taylor series does have a 0 at the beginning, but this next thing doesn't vanish. Right, we call this a 0 of order 1, or a simple 0. Okay, so that's the summary of the Archimedean analysis of the Riemann zeta function. But then there come this really remarkable thing that opens the door to doing some p-adic stuff. Right, you can't do p-adic stuff with real numbers. It doesn't quite work. But you can with q. And it turns out the values of the zeta function at negative integers are rational numbers. Now, as we said, the values of the zeta function at negative even integers are 0, right? And that corresponds with this formula here with the 1 minus n. But the rest of the values are not 0, and they are given by the sequence of Bernoulli numbers, which is a very exciting sequence. And I'm just going to, Bernoulli numbers is just easier to say than values of the Riemann zeta function at negative integers, okay? But that's really what I'm talking about. I'll talk about Bernoulli numbers, but the idea is that they are really the Riemann zeta function at these negative integers. Okay, so we have these values here, and I've written down the first few values of these Bernoulli numbers. Okay, but what defines this sequence? How should we think of it? All right, I'm going to ask for a more sort of deep characterization of this. They give an answer to this question, which you can see is quite classical. So people were working on this in the late 17th century. Right? What function of x calculates the sum of kth powers up to an integer x? Right? That's a fun number, like maybe number theories type question. Or maybe you think of it as like discrete integration. Right? So we actually know the formulas in calculus for integrating n to the k over n up to x, and that's got a nice formula, but it's a little bit more complicated once we ask for sort of the stepwise version of the same thing, integrating the function n to the k over n. And so because we know, right, because we know that the integral of y to the k dy is equal to y to the k plus 1 over k plus 1 plus c, right? So that suggests that this discrete summation should be close to that, right? We only have these sort of small pieces that are the defects. And that's why we actually expect that b0, right? So I put the k plus 1 over here, right? So I'm doing that thing that's close to the integral. So that's why you expect that b0 equals 1. And if discrete integration and continuous integration were the same thing, then the rest of the Bernoulli numbers would be 0, right? But they're not, because it's not the same thing. And the Bernoulli numbers are measuring, it was one way to put it, the difference, like the defect between discrete integration and continuous integration. Of course, they're also zeta values. They have a lot to them, of course. And a few other facts about what characterizes them. Oh, by the way, see, it's sort of interesting that this single sequence of numbers, right? It's a single sequence of numbers, but it works for multiple pKs with these sort of adjustments to the coefficients as you go. Sort of nifty. All right, a few other facts. This is something we call a generating series. Like there's a nice function involving E that determines the Bernoulli numbers as their Taylor series. And then this we might call a iterative definition of the Bernoulli numbers, right? So this is because this cancels out to 0, and because we know what binomial coefficients are, you can say, I want to know what bk is, and you can calculate it in terms of all the smaller indexed Bernoulli numbers up to k minus 1 using this formula. Okay, so this is actually a fairly good way of computing them in a computer, right? Start with b naught is 0, then use this. It's an iterative definition. Once you know the first k minus 1, you calculate the kth. Okay. And yeah, interestingly, these were discovered in 2 completely different cultures, but practically exactly the same time. Okay, they got the name Bernoulli numbers in the West. Okay. Now I want to start thinking about this p-adically. What's the idea? Well, there was a Archimedean sort of continuation of the zeta function, right? We extended it to all of C. Could we do that p-adically, right? And then let's just start with Z, because Z completes to ZP. So we're going to see, are there any congruences in the results? Okay, this is the first definition, which is interesting and ends up being interesting in multiple ways. We call a prime regulator a regular when it does not divide the numerator of these Bernoulli numbers for even n. Those are the ones that are non-zero, right? So the odd ones are just are 0, they're not interesting. for n's that go up to p minus 3. So when you start out with the primes, 2, 3, 5, 7, and so forth, they're mostly regular. But then you can see there really are a lot of irregular primes as you go forward. And it turns out, right, so the 691 I just wanted to highlight, because that 691 divides the numerator of B12, and we saw that earlier. Right, they start mostly regular. There seem to be irregular, and here's a frustrating thing. We actually don't know how to prove that there are infinitely many regular primes. We can prove there's infinitely many irregular primes. And it's sort of too bad, as you'll see soon. The conjecture is that they're both a percentage of primes as you go off to infinity, a non-zero percentage. All right, so why is it nice to be regular? It's because you can prove Fermat's last theorem. So this is why we sort of go back to number theory, and it's really interesting, okay? So Kummer did some remarkable stuff, p-adic stuff before p-adics really existed, because Kensel hadn't done it yet. If and only if there's an ideal in this ring of cyclotomic integers, right? So you take Z, where we do elementary number theory, you throw in this e to the 2 pi I over p. That's a pth root of unity, right? Its pth power is 1, but it's not 1. Okay, that's the kind of complex number that is. And it turns out for these kind of rings, you asked about things like unique factorization, and it turns out unique factorization only holds when every ideal is principal. And unique factorization makes arithmetic, like you might want to deal with to prove this, there's no non-trivial solutions in Z, a lot easier. But Kummer narrowed it down. He just needed to have no non-principal ideals that didn't go to a pth power and become principal. But this is actually characterized by being regular when you can rule that out. Okay? So irregular, you do have a prime that's not principal, and you, in this particular ring, which involves p as well, but its pth power is principal. And then Kummer used that exact property and said, okay, if I can rule out those bad ideals, And then I can do some work in that ring, Z adjoin the Pth root of unity, and get that there's no Z solutions other than those for which at least one is 0. One of those things is 0, which is just a trivial solution. Right? And so I just summed that up as saying it's like he could do it in the 19th century, right? As long as you had that simplicity of the arithmetic in that ring. So that really motivated a lot of interest in these things. But now let's just try to understand how p-adically nice are the Bernoulli numbers. So first of all, they're not too big. This is a first step. And I just want to say is that we perfectly understand the denominators of Bernoulli numbers. They're pretty much divisible by small primes as you start. And then it turns out we understand all the primes, right? So B6, it turns out a prime is going to divide the denominator of B6 even if and only if the prime minus 1 divides 6. Okay, so there's only 2, 3, and 7 satisfy that. And guess what? The denominator is 42. And we not only that, but we sort of know more about it. We know that when we add exactly these things, we get an integer. Okay, so in other words, denominators are under control. Why is that a big deal? Well, p-adically, denominators means that things get big. And we want convergence, right? I'm looking for some convergence, so that would be bad. So this is good news, right? The denominators are very much under control. That means the Bernoulli numbers don't get p-adically big. Okay, and then the next thing, which is a lot of notation, so I want us to take a little bit of time to take this in, is this pretty remarkable congruence, right? So being congruent, mod p, means that you're p-adically close, okay? That's the important thing here. So this is a p-adic closeness criterion. And then being close, being equivalent mod p to the a plus 1, that means you're much more p-adically close, right? As a goes to infinity, you'd be arbitrarily close. Okay, so which Bernoulli number, and then you have to divide it by m. So these are basically zeta values. Which zeta values are very p-adically close? Well, the zeta values are very p-adically close when their indices are p-adically close and the same mod p minus 1 as well. Okay, just throwing in p minus 1 in addition. All right, so as an example, I calculated out, let's say p is 5. Now 2 is equivalent to 10 mod 5 minus 1, which is 4, right? Because they differ by 8. And so we expect that what is this saying? This equivalence says that the numerator of their difference should be divisible by 5. And yes, it is. Okay, that's just an example. All right. And yeah, one interesting thing is it's not just a zeta value. There's also this extra thing being thrown in here, which I'll address in a bit. Okay, let's put it in terms of value. Let's go back to values of zeta. It's practically the same thing, but a bit more concise. Okay, so what did Kummer discover? Right, I'm going to go back to zeta value formulation, and this starts to look quite interesting. So when s and t, I want to evaluate the zeta function at these odd integers. Okay, and then it turns out if they're close p-adically and they're the same mod p minus 1, okay, then the zeta functions are also the same mod, also a high p power compared to using what you started. Once you do, oops, woo. Don't know how that happened. Once you do this extra little multiplier, okay, once you multiply by this 1 minus p to the s. At first that looks like a funny thing, but actually it's not so terrible because what we're doing is in some sense removing an Euler factor, right? So what was the zeta function? The zeta function is this multiplication of all the Euler factors. So when we multiply by this thing here, we're actually just removing one, if you like. Okay. Now what's cool about this is that it turns out that what we're saying then is that actually a p-adic continuity statement. So when we go on a bunch of numbers that are the same, mod p minus 1, so I fix an I, then as those s's get really p-adically close, the value of this zeta function times the Euler factor at p. Remove the Euler factor at p, gets really close. Okay? So it's when these get very close, then these zeta values get very close. And that's what you need to get a continuous function, right? This is sort of cool. It turns out, why would you expect this? That this condition, which I'll call star here, right? S and t being p-adically close and the same mod p minus 1 is exactly what you need to say that n to the s, or let's just do minus s, is equivalent to n to the minus t mod p to the a plus 1. So in some sense, it's interesting. We took the Bernoulli numbers as a sort of Archimedean extension of the zeta function to where the powers of the n's in the series here, right? S is negative, so these are actually positive minus s's because s is negative. And then what we're getting is that this is a standard thing in ZP that I would tell you about it earlier if I had more time. And then the continuity of the zeta function is behaving just like the continuity of n to the s. Oh, but there's a requirement. This only works if p does not divide n. Right? So star implies. Right? So star implies. So in other words, this is sort of reasonable that we need to remove this Euler factor. Powers of p don't do this. They're all over the place. Okay. So from this, we can actually get what we call a p-adic zeta function. So because it's continuous, it's valued on z, it goes to integers or rational numbers, you can actually say, hey, I'm going to, just like I sort of extended to the complex numbers, I can extend to a function like so. From zp to qp, right? We're going from z, which is contained in here, to zp because of that continuity. And this is called the Kubota-Leopold p-adic zeta function. Come up with in the 1960s. Okay. So when you ask about this, I want to say it's very much like the Archimedean world in some ways. So it turns out we actually can do analysis. There's p-adic analysis. We use power series. We can extend the radius of convergence by looking at the size of the coefficients, just like you might in complex analysis. These things have zeros only for irregular primes, where you p divided one of these Bernoulli numbers. So it's like, again, you can detect, this is this Hensel's lemma principle. You can detect when a power series will have a zero, and you can mod p. And another folklore conjecture, again, is that the zeros are simple. Okay, but what do they mean, right? And I think the zeros of the Riemann zeta function, they have a meaning. They're sort of like the frequencies of a Fourier expansion of the distribution of the primes. But what do these zeros mean? I think it's even more direct, actually. And also, I'm going to just tell you that it has a very concrete, once you know algebraic number theory, so I'm going to throw some algebraic number theoretic terms, it has a very concrete interpretation. So you can consider its power series, right? You just expand it as a power series where s is the variable. It can be considered to be an element of a ring with these are the coefficients, this is the variable. And then you can take these things that are called ideal class groups. These, like the x1, is taking exactly those things that Kummer was dealing with. So x1 is not 0 if and only if there exists one of these ideals in this ring. An ideal in this ring such that I is not principal, but IP is principal. Is a principal ideal. Okay. So these class groups sort of measure failures of unique factorization in these number rings. And then there's this main conjecture of Iwasawa theory that tells you exactly that these class groups, which come entirely from arithmetic, actually tell you exactly what the zeros are. Right? So this Iwasawa main conjecture says class groups know all of the zeros of these zeta functions. Sort of cool. All right, so this was established, this was proposed by Iwasawa, that's why it's called the Iwasawa main conjecture. It was proved by Mazur and Wiles in 1980, and they built upon some work of Ribbett in 1976, who sort of figured out the sort of x1 situation, and they extended it to x infinity. Okay, so to sum it up, some ways that p-adicity appears. How is it being used by people like me who are working in number theory? Basically, if we have a collection of mathematical objects, we defined over Q and Z, and that's sort of funny notation, terminology at first, we interpolate them. So what did we do that so far with? We interpolated Z, right? That's one thing. Or you can take, like, maybe you're familiar with like an elliptic curve equation. Like, I want to understand the like rational solutions of this equation. Right, so this is defined over Q. That's what the over Q means. I want to know the Q solutions. And then you could say, oh, well, if A and B are congruent mod P, maybe these two elliptic curves have something to do with each other because the equations are p-adically close. That's one thing we do. If it's number two, if it's defined over Q or Z and we want to study it, we can study it over QP and R to gain insight about its behavior. So the main first example of that is the Hasse principle. And that it gets extended to many other equations that number theorists like to study. And then finally, and this is a fun thing that I end up doing a lot, finite rings like Z mod P to the N are pretty easy rings. Like, continuity of functions into them is pretty simple. They're discrete topologies and so forth. But it turns out we can build up from these very finite characteristic things, Z mod P, and you can take limits. So we really do take limits of algebraic objects, like a function valued in Z mod P to the N. If you can make it compatible, then you can make a function valued in ZP, and now you're in a characteristic zero ring. And that can be really good news when you're trying to do certain things in number theory. All right, so thanks for your attention. I hope I've been able to convey some of the excitement in the p-adic world, and happy to take questions. Yeah.
So, just going back to the Riemann zeta function, like it's zeros, and particularly the real parts of the zeros tell you the representation of times.
Mm-hmm.
If someone were to show that all the poles were simple, or were to find a zero that wasn't a simple zero, like, does that also have like the number theoretic significance, or is it more just like a functional curiosity?
Yeah, I think in the Archimedean world, I know the p-adic world better on that question. So in the Archimedean world, I think there are some conjectures, and there's like reasons to believe, I forget if they're named conjectures. Maybe someone knows about the Archimedean world and simple zeros. In the p-adic world, what it would mean is that there's no common zero among all these F1s and even these Fi's. And so it just means that the module structure of these class groups is like very simple. So it really has a meaning. The sort of class groups are quite nice as you take them in this limit. Like these are really big rings, right? Cyclotomic integers where you would join a p to the nth root of unity, taking a limit, looking at their arithmetic. The simplicity of zeros would say that they have more niceness. Yes?
So at the beginning, you gave a few examples of characteristic properties of certain rings. R is the unique complete order field.
Mm-hmm.
Is there an analog of that for the p-adic?
Yeah, so the question is, R was the unique field with certain properties, is like QP the unique field with a certain list of properties? And the answer is yes. So I want to say it's something like it would be the unique, complete, characteristic zero field under a norm compatible with a norm. So unique normed field of characteristic zero in which powers of P converge to zero, something like this. And there's a theory I'll say if you want to Google something, local fields, right? So local fields are locally compact and complete fields with some of them are even characteristic P, like the field of Laurent series over a characteristic P field. And there's also R and C. So there's sort of an axiom system for which if you ask for the characteristic zero ones, they're all extensions of QP or they're extensions of R. They're called local fields. Another question, yes? Yeah, you. Yeah.
So I was going to ask you about a similar property for C.
Ah.
And I wanted to ask you if this is correct. So if you have a field that is harmonic of R characteristics, this embeds into C. And I think this easily characterize C because we have percentages. So the next question was.
Yeah.
So that's correct.
Yeah, so here's an interesting thing. Yeah, there is a theorem that says that any two characteristic zero algebraically closed equal cardinality fields are isomorphic. So thereby, it is actually the case that QP within its algebraic closure is abstractly isomorphic to C. They have the same cardinality. They're both algebraically closed in characteristic zero. But the topologies are completely incompatible. Did you have a follow-up question?
Yes. So the analog of the C over the p-adic would be the completion of the feature into there.
Yeah, exactly. So when you take R and then you go up to C, it's a quadratic extension, and you take an algebraic closure, right? But with QP, you take an algebraic closure, it's no longer complete. And it is actually a further extension to go to what we call CP, where CP is equal to first algebraically close QP. So QP was complete. Then you algebraically close it, it's not complete. You got to complete it again. Okay? And then you'd worry, does this keep going? Right? So it turns out, of course, it's contained in CPR, right? It's equal to it. Okay? So that's the good thing. What characterizes it? I guess it's algebraically closed. It's maybe the minimal algebraically closed complete field for which powers of P converge to 0 or something like that. Yeah. Yeah. So when people do p-adic analysis, they use this CP. Yeah. Yes.
Or we have this kind of miracle where it's algebraic closures like this degree 2 extension. Here we have this tower. Are each of these infinite extensions?
Yes. The completion, so this of course is a transcendental extension, because you've got an algebraically closed field. It turns out, yes, this is infinite, but it's quite understandable. So it turns out this is actually pro-solvable. So its Galois group comes from a bunch of steps which are abelian. That's not true of the absolute Galois of the Galois group of like Q bar over Q. So it's pretty understandable, but there's a lot of modern work in fields called p-adic Hodge theory, and a lot of Scholz's so-called perfectoid stuff has to do with ways to sort of understand this extension, make it geometric. Yeah, there's a lot of cool stuff you can do with the Galois theory over QP. So a lot of my work has been on that kind of stuff. Yes?
I guess like going on the last two more questions, if let's say you have like let's say you're given like some p-adic number, I guess how easy would it be to find like the square root or like some nth root of that number?
Mm-hmm. Yeah, so the question is, if you have a p-adic number, can you find an nth root of that number? And the answer to that is that sometimes it's not too hard to figure out, especially when n is relatively prime to p. So maybe I'll answer that. This is this cool statement called Hensel's lemma. If you have some fx, that's a polynomial in ZP, and then if you have some solution, so f of y equals 0 in say fp, where y is an element of fp. So if you have a 0, and then it's not a double 0, so it's a 0 of order 1 mod p. Another way of saying that is that its derivative is not. Then the fact is that there exists a unique y tilde in ZP such that f of y tilde equals 0. So under this extra thing about mod p, you have no double 0. You just have a single 0. You can lift it uniquely. Now, how is that useful? Well, that means that if you first have x to the n minus 1, and you want to understand x roots of, say, 1, or maybe something else, but let's start with 1, then you can just see, does it have solutions in a field? And as a result, you can actually show that what I call mu p minus 1, the p minus first roots of unity, are always contained in ZP. Why? Because the p minus first roots of unity exist in FP, because FP cross is this cyclic group. It has all the p minus first roots of unity. And those lift, because of this Hensel's lemma, to ZP. So this is funny, right? So somehow there's a list of integers that converge to a p minus first root of unity. So like in Z11, the 11 adic integers, there is a 10th root of unity that you can reach 11 adically with a sequence of integers. So yes, finding roots is much easier in p-adic world than in, usually. You don't always have to take extension.